All right. Huh? If someone is asking me something, I can't hear them. So Miss Saldana, if you can just interrupt me. All right. So we are going to go over.
You should have said, never mind.
Okay. Got to speak loud. Got to speak proud, Yusra. Okay, we're going to go over 2.3b, which is kind of not that long, and then 2.3c. Okay. So 2.3b is about the big misconception surrounding Newton's first and second laws. What is it from your notes? Do you remember? No one remembers from the reading? Can you hear me again, Miss Saldana, or no?
Yeah.
Okay. So no one remembers then, is what you're saying. Okay. The big misconception is the idea that motion requires a continued force. It's the idea, are you all writing notes, I hope? Because you obviously don't have good enough notes to tell you this information. So maybe you should be writing notes as we're doing this. It's the idea that sustaining, what does that mean? Does no one know what the word sustaining means in this situation? Okay. Sustaining means maintaining or continuing in this situation. The idea that sustaining motion or keeping motion, maintaining motion, requires a continued force. Newton's first and second law, or Newton's first law specifically, says this isn't true. What does Newton's first law state? Oh, you have to talk way louder. Yep, exactly right. So Newton's first law states that an object in motion will stay in motion. Does it say an object in motion needs a continued force in order to stay in motion? No. It says an object in motion will stay in motion, or an object at rest will stay at rest, unless an unbalanced outside force acts upon it. So it doesn't say anything about needing to have an applied force the whole time. And if we think about this, like think about a ball rolling. Remember Galileo's experiment where he sent the ball rolling down the U-shaped ramp? Was there a continued force? Was there an applied force the whole time to make that motion keep going? No, there wasn't an applied force at all, right? We dropped the ball and it rolled and kept moving. So the idea that motion requires us to constantly put a force is not correct. Okay, so let's see if you're infected with this misconception. So we have two students. Please pay attention because I'm going to ask you a question about this. Two students are talking about their physics homework, okay? And they're talking about an object that is being acted upon only by two individual forces, and they're both in the vertical direction. So the two forces, we have this object, here's the free body diagram. We have the normal force, and this is going to be equal to 20 newtons. And we have the force of gravity, and this is going to be also equal to 20 newtons. Okay, so this object has only these two vertical forces acting upon it. During this discussion, student 1 says that the object could be moving, and he says that this, if friction and air resistance are ignored, then the object could even be moving in the horizontal direction. If we're ignoring the student number 1 says if we ignore the friction force or if they're negligible, and if we ignore air resistance force, if those two things don't count, he said that the object could be moving in the horizontal direction. It could be moving this way or this way. That's what student number 1 says. The second student, same situation, they're having an argument about this. The second student says that the object couldn't have any horizontal motion because there are only vertical forces acting on it. So student number 2 says no horizontal forces means no motion. All right. And he says that the object must be at rest, maybe on a table or a floor. It has to be definitely at rest. So, are you asking?
You said, can you go back up on the slide so she can see what you wrote?
I can go to right here.
Yeah, right there, she said.
Okay. So we have student number 1 saying if friction and air resistance are they're negligible if we don't count them, or if they don't exist, if they're so small that we don't have to consider them. Motion, horizontal motion particularly, horizontal motion could be occurring. We don't have enough information to know. And student number 2 says there's definitely no horizontal motion because there's no horizontal force this way or this way. So think about it for a second. And based on this big misconception, based on this idea that I'm telling you that there's all of 2.3b, which one of these students is correct?
She said student 2.
You are infected with the misconception. What is the misconception, whoever said student 2?
What's the misconception?
It's written right here. Right. So in order for there to be motion, the misconception that the incorrect idea is that in order for there to be motion, there has to be a continued force. That's wrong. That's not correct, because Newton's law says that motion will continue in the same velocity, meaning the same speed, the same direction, whether or not there's forces acting on it. It will continue the same with no force acting on it. Right? So we have to break this in our heads. This is the misconception that I think some of us we're obviously living with. So student 2 is not correct. Student 2 has the misconception infection. Student 1 is correct. Think about an object falling from the sky. Does that object have an applied force? They would only have either air resistance or the force of gravity, right? There's no applied force. We don't have to have a force applied this way in order to have this motion occurring. Let's think about this as a ball rolling on the floor. And let's say there's no friction at all. Let's say that I'm in a lab and I am Rick and Mortying it, and I have this frictionless surface. There's no friction on the surface. If I roll a ball, if I push the ball and let go, what will that ball do? Anyone? No one do you not understand what I'm saying?
No, draw. Andrew said it will fall.
So I have a ball and it's gonna roll on this surface. I push it with my hand and then I take my hand off and it rolls. And it's gonna roll on this surface that has no friction whatsoever. This involves a little imaginary thinking. So I'm sorry, you have to use your brain a little bit. Maybe it's a little early for that, I'm sorry. This ball, according to Newton's law, will this ball stop? No. How long will it go on like this at the same exact speed and velocity, or the same speed and same direction? Forever. It will go on forever until an unbalanced force acts upon it. Is there an applied force on this ball right here? Am I applying a force to it?
No.
No. Is there a force of gravity on it? Yes. Is there a normal force on it? Yes, because it's not falling through the table or the surface, right? It's not moving up and down, right? So this could, let's say the normal force on this ball is 20 newtons. And let's say the force of gravity on this ball is 20 newtons. Are there any other forces? Nope, because there's no friction and no air resistance. So is this ball moving forward though?
Yes.
Right, so which student is correct?
First one.
Number 1, exactly. So I totally understand. It's like a really hard, weird thing to understand, right? Especially because we talked so much about unbalanced forces and unbalanced and balanced forces. But the misconception that we have to break in our heads in order to really understand Newton's second law is that we don't have to have a force applied constantly in order to have motion. But what we do have to have, if acceleration is occurring, meaning if the ball is speeding up or slowing down, do you think we need a force for that? Before you blurt out an answer, think about what it would take if I wanted this. Let's just look at this ball again. If I wanted to speed this ball up, is it going to speed up on its own? No. What do I have to do? Exactly. If I want to slow this ball down, I could also I could introduce friction to this surface, right? If I introduced friction, that would cause an acceleration, a negative acceleration, a deceleration, right? So in order to cause acceleration, then we have to apply a force. So if acceleration is occurring, a force has to be being applied. That's a weird way of saying that. A force is being applied to the object. So motion is not, let's just sum up this really quickly. Motion in general is not evidence that a force is being applied. The way that we can determine if a force is being applied is if acceleration is occurring. Acceleration is evidence that a force is being applied. So let's look. I'll give you a second. Are you writing this down? Are they taking notes, Miss Saldana? I can't see them.
Yes. Yes.
Oh, good. Thank you. All right. 10 seconds. Okay. Can I go on?
They
Okay.
said yes.
All right. So let's think about one more thing here. I have an object that's traveling at a constant velocity. Actually, we'll say at a constant speed east. This object, what can you tell me about the, let's say that it's let's say that it's a car and it's coasting. Do you remember what coasting means? It means just rolling. It's coasting eastward, maybe down a ramp, a little hill. Okay, so the car is traveling east that way. All right, constant speed and not changing directions. What's another way of saying that?
What'd she say?
There is a constant velocity, then the acceleration is 0.
Exactly, acceleration is 0. So what can you tell me about the forces acting on this car?
Gravity, non-force.
Gravity and normal force. Is there an applied force? Is there a constant applied force to this car? No. No applied force because acceleration is 0. All right. What about this car speeding up from 45 kilometers per hour to 75 kilometers per hour in 1 minute? Do we have a change in velocity? Yes. We're going from this speed to this speed. So velocity is changing. What does that mean about acceleration? Yeah, in this situation, it is positive, or we could just say that acceleration is occurring. It is positive, that's correct. Positive. So what does that, what?
They said it was constant.
Velocity is constant?
No, acceleration. If velocity is changing, then the acceleration is constant.
Yeah. It can be yes, acceleration is constant. So, but is it 0?
No.
No, it's occurring. Acceleration is occurring. It's speeding up, so we're accelerating. So what does that mean about a force? What are the forces acting on this car? There is a force acting on the car, right? There's an applied force. The applied force would be through the engine, actually, in this situation. So yes, there's an applied force, right? Okay. I just want you to understand the connection between these things because it's really important that we don't get confused about this. Okay, does anybody, that's all we have to talk about for 2.3b, but I want to go on to 2.3c. Does anybody have any questions about 2.3b?
They said no.
Great. All right. Okay, now we're going to do 2.3c. All right, we're going to introduce one new equation here. So in this section, we're going to determine the acceleration of an object if we're given all of the magnitudes of the individual forces acting on the object. So we're going to be given a free body diagram or a word problem, just describing the forces. And then from all that information, we're going to take that information and figure out the acceleration. Okay, so we're going to need 3 equations. So the purpose, let me write that.
Ms. Montgomery,
Yes.
did you create the test?
That has nothing to do with what's Okay.
Yes, you got it. You all got zeros because you asked.
Where is your this?
Okay. So determining the purpose of what we're doing is we're going to determine the acceleration given all of the forces acting on the object. How? We will use three equations. There's three different equations we can use. We're not necessarily going to use all three at once, or we're not going to use all three in the same problem, but there are three equations that we can use in order to determine the acceleration. All right, the first one, we know the first two. The first one is the net force equation. What does net force equal?
Mass times acceleration.
Mashallah, good job. Yes, exactly. The second equation is the gravitational force equation. What's that?
Fg equals mg.
Whoa, 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 whoa. My mouth feels like the desert. I'm sorry. Yes, Fg equals mg. What's another name for that equation? What else? What's another word for Fg?
Gravitational force.
And another word for that?
Force of gravity.
And another? It starts with a W.
Oh, wait.
Good job. All right. Our final equation that we're going to need to use is called the frictional force equation, which we have not learned yet. So I'm going to give you the equation and then I'm going to explain the parts of it. So friction force equals this symbol called mu. Whoa, I just messed up all of that. Okay. Mu times the normal force. All right, that's the equation. So let's break it down and look at what each component is. This mu is the symbol is mu. The Greek letter is called mu, but it's called, in this situation, it's called the coefficient of friction. Coefficient of friction. All right, and from your reading, does anyone know what that is or what that means?
Friction.
Friction, not quite.
Friction.
So there is a maximum amount of friction that a surface can exert on an object. For example, this surface of this book has a certain amount of friction, right? The surface of my wall has a certain amount of friction. The surface of my floor has a certain amount of friction. The surface of ice, the surface of glass, the surface of a mirror, they all have different amounts of friction. If you think about sliding a box on all of these different surfaces, some surfaces are going to be easier to slide on, right? Like ice or glass would be easier than sliding on carpet or dirt, right? So this coefficient of friction is a constant that's experimentally determined, meaning it's, constant, experimentally determined. So what that means is for every surface, like glass or ice or whatever you're looking at, it has a constant number associated with it. Like, it's like pH. The pH of lemon is, let's say it's 1. That's experimentally determined. We took lemon, we figured out what's in lemon, we measured the acidity of the lemon, and we found that its pH is 1. but the pH of bleach is 11.4. That's experimentally determined. It's a characteristic of bleach that its pH is 11.4. So it's a characteristic of glass that its friction or that its stickiness or the way that it interacts with other objects, the force of friction that it has is, let's say, 0.2, whereas carpet, let's say, has a coefficient of 1.3. Do you understand? So the higher the coefficient, the higher this value of mu, the more friction this surface has. Do you understand what I'm saying? Let's look at an example. Like I said, this is made up. I don't know the actual values. I don't have I'll give them to you when we do the problems, but let's say glass's coefficient of friction. I'm not gonna write that all out. I'm gonna write glass's mu is equal to 0.21. Whoops. Okay. Let's say that carpet, why am I writing glass again? Good grief. Carpet's mu is equal to 1.33. Okay, so these are values, these mu values, you aren't expected to know them. I have to give them to you. It's a constant associated. Are you laying down, whoever that is on the left? Don't you lay down. The mu is given to you. It's a constant associated with the surface of the object. Okay, so carpet has a really high mu. If it has a high mu, that means that it has a lot of friction. Glass has a low mu, meaning that there's not a lot of friction. So when an object, any object, let's say a box, a cardboard box, if I'm going to slide a cardboard box across glass, it's going to be easier than sliding that same cardboard box across carpet because carpet has more friction. It has a higher coefficient of friction, a higher mu than glass does. Another way of thinking about this is that mu gives the relative amount of, you can think of it as attraction or adhesiveness or stickiness between two surfaces. Relative amount of adhesion or attraction or even stickiness between surfaces. So I'm just giving you that as another, maybe if you're still a little confused, hopefully that will clear it up. All right. Okay, so this frictional, this mu is going to be given to you every time. So we can use these three equations. Whoops. We can use these three equations in order to determine the acceleration. We can use one of them. Uh-oh. They left. Resume my recording. Okay, so we're going to do an example problem for those of you that didn't hear me the first time. So we have an applied force of 50 newtons is used to move an object to the right across a frictional surface. So there is friction across a frictional surface. All right. The object encounters 10 newtons of friction. All right. Let's draw a diagram to determine, we want to determine the normal force. The net force, the mass, and finally the acceleration. So I'm not going to break it down this much for you when I give you the problem, but as we're doing this example, we're going to have to find all of those things in order to find the acceleration. Okay, so does everybody have the problem written down and understand what we're trying to find? Let's draw. Oh, we can neglect air resistance. Or the force of air resistance, okay? Okay, let's draw what this might look like. I'll draw it right here. Okay, so we have 10 newtons of friction force. So I'm just gonna put it going to the left because we said that we have 50 newtons of applied force used to move an object to the right, right? So we're gonna have an applied force of 50 newtons to the right. We also have a force of gravity, and we have a normal force. In this situation, we're not, you don't need to find force of gravity because I'm asking you to find the mass. So what I'm going to tell you is that the force of gravity equals 80 newtons. All right. So let's find the normal force first. That's the easiest to find. This object is only moving to the right. It's not moving up or down. So what is the normal force? Yep. Good job. So this equals 80 newtons. All right. What about the net force? 40 newtons to the right. That one's easy too, right? Because we're going to be just subtracting 10 from 50. So this equals 40 newtons to the right. All right. What about the mass? So first of all, let's think about why we're solving for all of these things, or why we're thinking about all of these things. I asked you to find the normal force because we need to just finish our free body diagram, and we know that the object isn't moving up or down, so we have to cancel. We have to kind of take that out of our consideration, and we also will need to know the normal force if we need to use which of these three equations. Do you remember? You remember the three equations I just wrote down that I said we're going to need to use them in order to solve for acceleration?
Yes.
Right. So
They said,
say again, Ms. Solana?
they said yes.
Okay. Which of the three equations requires us to know the normal force?
The first equation. No, the third one.
The third one, the friction equation, right? So that's why we're just gonna find the normal force, because you know that we're gonna need to use these three equations in order to find acceleration. Given the information that I've been given, I can't find acceleration without finding all four of these things, or all three of these things first, right? So that's why we needed to find the normal force, because maybe we're gonna use the friction equation, and we need to know the normal force for that. Why do I need to know F net and mass?
Find the acceleration.
Right, because I can rearrange the net force equation in order to solve for acceleration, right? Okay, so what is the mass? Let's solve for the mass first.
Mass is 8.16.
It's what?
8.16.
How'd you get that?
I did force of gravity over 9.8.
Good job. So we get Fg divided by G equals mass. So what are those numbers? We have 40 newtons.
8 over 9.8.
Good job. All right. And so what did you say the mass is?
8.16
Eight?
8.16.
No. 40 divided by 9.8.
It's not 40, it's 80. The net force is 40.
You divide 40 divided by 9.8 is 4.1 kilograms.
But where did you get the 40? Isn't grab
This is the force. This is net for. Oh, sorry. Yeah, no. Yeah, why did I write 40? Good job. I was writing net force. I'm sorry. Good job. Wow, who is talking just now? Was that you?
Yusra.
Woo! Good job, Yusra. Thank you. Way to stick to your guns, by the way. You're like, no, Miss Montgomery. Yes, that makes more sense then. Good job. Okay. So for your homework, actually, instead of doing the practice problems that I have posted, I want you to finish this problem because we have no more time. So I want you to find the acceleration of this. Okay? And I want you to post it in Google Classroom. All of your work. I want you to show your work. Take a picture of this that we did and give me your acceleration. Okay? All right. Thank you.
Thank you.
Thank you.